So now that we've explored the properties of stars and we have a powerful tool in the HR diagram to understand them, it's time to turn our attention to the life cycles of the stars. In other words, how are they born, or how do they form? How do they live? And interestingly, how do they die? Well, in this lecture we're going to explore star formation or stellar birth. So where do stars come from? Well, the story begins as we look out into space. We see enormous clouds of gas and dust. Oftentimes we take photos of those. They have very beautiful colors to them. But this is the raw material for stars. We call it the interstellar medium. And it turns out if we wanted to analyze it, we would find it's approximately 70% hydrogen and 20% helium and a little bit more of the other elements as well. Now in some areas out in space, this interstellar medium is denser, more concentrated together. And here's where stars can form. We first, though, need to define what is a star. I mean, we saw that it was actually a large spherical object, very hot, of gas, but it's important for us to define a star as an object that generates energy by nuclear fusion, as we discussed in our previous lecture. So how does a star begin to get to form energy by nuclear fusion? Well, clearly it needs to get very, very hot in the center, doesn't it? And again, here's where those large clouds are going to come into play. By the way, again, we can look out into space and see areas where the gas and the dust is very dense. Oftentimes it will block starlight in the distance, and we'll see somewhat of a black silhouette where there doesn't appear to be any stars. Well, actually, again, it's a very dense region. How could we ever know what's happening inside the cloud? Well, as we'll see in a minute, we're going to model that, but interestingly, different wavelengths of light allow us to peer into the cloud. Visible light may not penetrate, but infrared light often does. So that's a powerful method for astronomers to use. So how does the process begin? Well, in a word, it begins with gravity. Gravity is really the driving force behind star formation. Now, gravity is a very weak force, actually, and so as we picture these clouds out in space, some are a little denser than others. Two conditions are very important for stars to form. Number one, the cloud has to be relatively high density. And number two, it has to be a relatively low temperature. Why is that? Well, if you think about it for a minute, we have gravity, a very weak force. The higher the density, in other words, the more particles there are with gravity to pull on each other, the more likely they will form a star. And likewise, if the temperature is too high, that means our particles are moving fairly quickly, and that means that gravity will not be able to contract them together. So thus you can see we need a relatively high density and a relatively low temperature. So as astronomers want to study places where stars form, they naturally focus in on clouds that are cold and dense. Now there's a number of steps that we're going to talk through here that occur. This is a very detailed process, but let me just basically walk you through that. Gravity, again, being the driving force of this enormous cloud, begins to slowly contract. Now as it does so, gravity is taking the particles and they're beginning to move just a little faster. And we would interpret that as being a slightly higher temperature of the particles. Well, again, here's where we need that higher density to keep gravity winning the battle, so to speak, because as the particles increase their temperature, they're going to tend to want to fly out of the cloud. So at first, there's a little bit of a battle, a little bit of a balance going on here. Will gravity overcome the higher temperature and the process continue, or will it not? As the temperature rises, so does the pressure. So again, gravity must continue to do its work. There may well be some places where it cannot do that, and we simply won't form stars. But when gravity can overcome the temperature and the pressure and begin to continue to collapse that cloud, here's where the cloud will begin to change. Now, of course, any such cloud is not going to be perfectly uniform, is it? We can't imagine that. Rather, there will be areas within the cloud that may be a little denser than others, here or here or here. Here's where gravity really goes to work. The slightly denser regions will have slightly more gravity, and they will contract slightly more and continue now to pull in more additional matter growing in mass, growing in density, and yes, going to fragment to form new stars. So essentially, we shouldn't picture this cloud again as nice and uniform, but rather very clumpy, in which there's certain regions where the stars are going to form. Here's again where gravity has enough mass to do its job and form stars. In fact, most of these clouds that we do see out in space often have enough material, enough mass, to make hundreds of stars, sometimes thousands of stars. Now, these stars won't all be identical to our sun. We mentioned in our last lecture that some are very much larger mass or lower mass. So there'll be a wide variety of different masses in such a cloud. Well, as gravity continues to work, the cloud begins to shrink and it begins to fragment into individual pieces that will eventually turn into stars. Three important things happen based on the laws of physics. Number one, we already mentioned that the material is going to heat up. In other words, the gravity is going to pull the particles closer to each other. That gravitational pull is going to increase slightly, and therefore their speed is going to increase slightly. And you and I would measure or interpret that as additional heat. So our cloud is heating up somewhat. Number two, as gravity contracts the cloud, a process of angular momentum is going to take place. We mentioned that briefly in our first lecture. Picture this large object, maybe moving very, very slowly, randomly, but as it shrinks, it will find a particular preferred direction of motion, and we will begin to get a circular or angular type of motion in the object. The third thing that's going to happen is that as that cloud begins to spin, gravity, of course, is pulling it together in all directions, but the direction of spin, or rather I should say perpendicular to the direction of spin, there's going to be a slight centrifugal force pushing the particles outward. Very much like if you take a spherical lump of pizza dough and spin it and throw it up in the air, what's it going to do? Well, it's going to flatten. So our cloud is going to heat up, it's going to spin faster, and it's going to flatten. Now, gradually, of course, most of the material will work its way to the center to form our young star, but interestingly, there will be some material left over in a flattened disk that someday may form planets. Well, if our idea is correct here, is there any way to confirm that? Is there any way to find evidence of it? Well, in recent years, we now have the ability to do just that. We can look out into space at areas where we think that stars may be forming, and sure enough, we can find young objects with disks of material around them. I'm going to show you a couple examples here. In one example, you'll notice a object seen kind of edge on to the disk, and it appears exactly that, as a flattened disk. Astronomers have removed the light from the star because it's so very bright that it would overwhelm the disk, but you clearly see a flattened disk seen from the side. In the second picture, you'll notice a very similar looking disk, but here we're looking down from above at a different angle. And again, we clearly see this disk of material around the young star. Well, this is strong confirmation of our ideas about how stars form. Well, as time goes on, that center of the object gets hotter. Gravity pulls it smaller, contracts it more, it's getting denser and hotter. And sure enough, at some point in the very center of that cloud, it's going to reach a temperature where nuclear fusion can begin. Now, the very lowest or minimum temperature for that is approximately 10 million degrees Kelvin. Quite a high temperature. Our sun has a core temperature of approximately 15 million, and other stars maybe even more than that, but the minimum temperature there that's required is 10 million degrees Kelvin. At this point, these reactions begin, and although our cloud has been contracting and contracting and contracting, now there is a tremendous increase in the energy released that stops that contraction. We get essentially a burst of energy. Sometimes we use the word the ignition of the core. This stops the contraction. The star may expand a little bit more and oscillate a bit, but at some point it begins to stabilize. The pull of gravity inward with the flow of energy outward find an equilibrium, and we have a young star. The energy produced is balanced by that gravity. Our star is on the main sequence. Now that star, depending on its mass, may take varying amounts of time to go through this process. The very most massive stars go through this process quite quickly on astronomical scales, perhaps as little as 1,000,000 years or so. But the lower mass stars take considerably longer, tens of millions of years often, for them to form. So we may expect to see stars at various stages of formation. If we look at a particular cloud, we'll see again different stages. The more massive stars forming more quickly, and the lower mass stars forming more slowly. How small of a star can we make? And how big of a star can we make? Well, it turns out, we mentioned previously, there are limits to that. We mentioned that the very lowest mass of a true star is about 8% of the sun. Why is that? Well, at that breakpoint, so to speak, our star has a very relatively small amount of mass, and therefore a relatively small amount of gravity or strength of gravity, and it can only compress its core so much. The core may not reach that important breakpoint we set of 10 million degrees to start the nuclear fusion. Well, if it can't start nuclear fusion, it's not a true star. Now, we have found a few objects like this that are just simply too small to be a true star. Their core does not produce energy by nuclear fusion because they've, again, not reached that 10 million degree temperature. And again, the magic point there, about 8% of the sun's mass, and these objects we call brown dwarfs. What is a brown dwarf like? Well, it's a fairly small object, and it's somewhat warm because of its contraction, but again, in its core, the nuclear reactions are never ignited. And as a result, it's relatively warm, perhaps 1,000 degrees, possibly as much as 2,000 on the surface, and it just never turns into a true star. So we can actually see a few of these. They're very difficult to observe because they simply don't give off much light. So that explains why stars can only be so small. How about the greatest mass stars? How large of a star can nature make? Well, here we have the opposite problem. We have so much mass and so much gravity. That core is heated tremendously, many, many, many millions of degrees, even hotter than our sun's core. And as it does that, of course, it's pouring out enormous amounts of energy. Well, such a massive star naturally would have a very large radius, but the material at the surface of the star is quite a distance from the center, and therefore it's held weakly by the star's gravity. But meanwhile, you have a tremendous amount of energy pouring out of the star, essentially providing a force outward. It's literally going to blow the outer layers of the star away. So here nature finds again a balance. The star can only have so much mass before it begins to shed its outer layers because of all of the energy that is being released. And that magic number, I think we mentioned, about 150 times the mass of the sun. Now, interestingly, nature doesn't produce low mass stars and high mass stars and medium mass stars in equal numbers. It produces many more low mass stars than medium mass stars, and many more of those than the high mass stars. In other words, the high mass stars are very rare. The conditions are such during this process that it's more difficult to create a high mass star, and it's far easier to create a low mass star. So we find quite a few more low mass stars than high mass stars. If we were to look at our HR diagram, we'd see something like that. We'd find very few of the high mass stars at the top of our main sequence, but we would find countless low mass stars down at the extreme lower end of our main sequence. So nature tends to make many, many, many more low mass stars than high mass stars. They're simply more common. Well, this gives us a first nice introduction, a nice overview of stellar formation. In future lectures, we're going to continue on and see how the stars go through their life cycles, and at some point, again, begin to change. We'll see some very dramatic changes in the stars as they use up their essential fuel. Different physical processes will begin, and our star will go through various changes, and as we mentioned, we'll see it move on our HR diagram. But for now, let's go ahead and do our summary on stellar formation. We began by looking at where stars form, And we discussed these enormous clouds of gas and dust out in space, often called a nebula. And here we need a cloud with a relatively high density and a relatively low temperature so that gravity is able to contract the cloud down. The cloud will then begin to fragment, and the cloud will break into smaller pieces where gravity can continue to contract it denser and denser. How do stars form? Well, at some point, those fragments, again, as gravity contracts them, are getting hotter and hotter in their centers. And at some point, that magic 10 million degrees Kelvin, nuclear reactions can begin. Here, the star now has a burst of energy to stop the contraction and balance gravity into a stable spherical star. The star finds an equilibrium point. We're able to look at its luminosity and its temperature and plot that on our HR diagram. We saw that stars can only be certain sizes. At 8% of the sun's mass, any lower than that, the star simply doesn't have enough mass and enough gravity to compress the core enough to get it hot enough for the 10 million degree number to create nuclear fusion. So we don't have any core fusion. We don't have a true star. On the other hand, at the high end of the scale, we saw that any star that has more than 150 solar masses is pouring out so much energy that its outer layers, being weakly held, are literally drifting off into space. And as a result, again, we don't have a stable star. So what an interesting story we see here. How stars form. Gravity doing its work over many millions of years in these enormous clouds. Again, we're not able to watch any one particular star form, but we can see them at different stages of development, piece that together, and begin to understand the life cycles of stars. So I look forward to our next lecture where we'll see more concerning the stars' lives.